In this video, I will be talking about the design of the first arm, second arm, and slide for Team Light's 5-axis arm project from the 2023 off-season. Now, why is it all of these three different mechanisms all in one file? Ideally, it could have been separated into further files, but considering how integrated I imagined the gearbox would be, I thought it was best to just include all three mechanisms in one file. Also keep in mind that this entire project was done by myself and one teammate who walks a car, so it was possible to just not divide the robot into too many files, and I was tasked with making that many parts of the robot, so I could put it all into one file. Now, in these kinds of more complicated projects, usually it's involves more members and dividing the work further. So considering that, you would have to probably divide the files even further, and you'd have to just keep in mind that things are actually integrating together, and that won't be as quite straightforward as if when all the things are in one file as it is for this walkthrough, but it's definitely very doable. I mean, I integrated this file with the turntable file, and I did that by just making sure the dimensions lined up, and when in doubt, checking the master file. Okay, so what did I actually imagine? The key part of making such a complicated 5-axis arm actually work is that you have to think about trying to motorize the different joints. Okay, so I'm gonna transfer over to Miro and try to draw some things up. Okay, so if we think about this, there's one pivot here. Unfortunately, I don't have my original drawing from the very first video anymore. There's one point here, and there's going to be a second pivot here, and then effectively there's some kind of slide, right? And to motorize these different points, well, this one down here is pretty straightforward. We can just stick on some kind of standard gearbox. But this point over here, there are two options. One is to put the motor beside the actual joint, just have another very standard gearbox there. The problem with this is that now the weight of a big portion of the weight of this entire arm is going to be around that pivot, and that puts more strain on this first arm to be able to maneuver it. So if we want to move that gearbox over here, we're going to have to chain or pulley drive this second arm's pivot all the way from down here. And to do that, well, there's only really one way. The chain would have to follow the exact same path as the arm. You think about it, and it does something different, like maybe we put another gearbox here, and we chain this. This is not a static component. In another position, the arm is now up here, and our gearbox is still down here, and now this chain is broken, or at least no longer actually driving that second arm's pivot. So the only realistic way to do this is to have any kind of chain or pulley path follow the actual arm, so that when the arm moves, you can still drive that second point. And, well, effectively the third point is a linear slide, but it's going to be the same idea. It's going to have to be driven by some way, by assuming I don't want to put the gearbox up here, and that is what I decided. I wanted to keep the weight as much as possible at the bottom of the robot around where the turret is. You would have to have some kind of chained pulley system that follows the path of the actual arm in order to make this all function. Okay, so that's going to become more clear if you don't really understand what I just said, but that's kind of what I was thinking going into this. And the key thing here is simply that all three of these different mechanisms, gearboxes, are actually going to be centered down here around this first pivot. Okay, they're all going to feed into one axle, as crazy as that might sound. So what was I thinking when I went into this? My very first thought was, okay, I have, by the way, these two rectangles down here are just reference points for the two pieces of 1 by 1 inch stock on the turntable. Okay, they're just distanced the correct distance apart, I suppose. My first thought was that we were going to have to just, I guess, sandwich the 1 by 1 pieces of stock with 2 plates. And this provided some additional space or something like that. I guess now looking at this file, if I remember, I'm starting to remember a bit better. The idea was something like one side could have these 2 motors. This is all according to our calculations that we did for the first arm pivot, right? It's based on 2 motors, as you can see. Number of motors is 2, right? This is the gear ratio, blah, blah, blah. You know, it would have to use a triple stacked planetary gearbox with an additional layer of gears. And then I decided that instead of forcing the motor to hold the mechanism in place, you could use some kind of pneumatic brake to do that a bit more effectively without relying on electrical power and just using air pressure. And so one side would have that gearbox, the other side would have the other gearbox. But looking at that, I realized that if I did it in this kind of way, there were kind of 2 problems. The first is that there is not quite enough room to put, at least comfortably put an arm down the middle of here between what would be essentially some kind of mirror image, like it would have motors on the outside and pneumatic brakes on the inside. And the second issue was that doing this in such a way, I decided wasn't very smart, because if we think about the turntable, the inner edge of the turntable it actually has a plate under here, right? So this plate for the gearbox would be putting its weight on that plate. That's relatively stable. This plate is just being held in place by 3 bolts. And yes, bolts are very strong, but it's still only 3 bolts. And this is a lot of weight, like really a lot of weight for all these gearboxes. I also didn't like the idea of trying to run an axle through 4 different plates. It just makes it harder for me. It's definitely possible. It does create more support, I suppose, for that axle, but it makes it very difficult because it means mechanical has to perfectly align these 4 plates to get that axle through smoothly, and that's just something that I find can be very hard to do in practice. Question might be, why am I double layering gears here? When your torque is this extreme, your gears can actually shatter. Case in point, I've inserted a picture here that shows you a gear I shattered once when I was using, I believe,
About a 400 to 1 gear ratio.
now to be fair, these are aluminum gears and not the steel gears that I intended to use in this kind of design. But that being said, steel gears probably can also shatter under enough force applied to them. So a way to make the gears not stronger, but to distribute the force applied on the gears is to double layer the gears. That just makes it so that they're a lot less susceptible to getting damaged in such a way. Okay, so after doing this short CADing sprints, I went back to thinking through this design, trying to visualize it in extreme detail so I could just execute it and not have to do so many iterations. But as you can see, I ended up doing essentially 3, and I will be covering more than 3. Like, I'll cover increments of these 3. Okay, so what did I imagine? I decided that what would be ideal is to have this kind of static plate that is in between with these 2 plates on the inside of the 1 by 1s. I would have the first arm, and that's its pivot is actually down here, being driven by these 2 motors down below the point of rotation, and then I could put the pneumatic brakes over here, so there's nothing in the way on the inside, and that frees up a lot of space for me to put all the other pieces that you're going to see are required to make this actually work, because again, everything has to go through this center axle that this gear and this bearing are running off of. Everything's going to have to go through this axle and get powered in some kind of way, and you'll see what I mean by that. So the next part of this was, okay, this bottom arm is being driven by gears. So that's pretty straightforward, pretty simple, you could say. I mean, it already looks pretty chunky, but this is by far the least complicated part of the gearbox in question. The next thing I wanted to do was that I needed to figure out how to power this second arm. And I decided the best way was to have some kind of chained off sprocket. And you basically need to have something that goes through the axle, but doesn't actually rotate with the axle. Because if you think about it, you don't want the second arm, you only want the second arm to move when you want the second arm to move. If the sprocket or gear or pulley or whatever system you're using to drive the second arm has a hexagonal inner bore, that means it would have to turn with this axle when the first arm turns, because, well, that the first arm is going to turn when this axle turns, because it's being powered by these gears that clearly do have a hexagonal inner bore. Okay, so considering the parts that, at least at the time this robot was designed, the only option for choosing a kind of rotational piece that has the ability to put a bearing in it so that you can then have a smooth bore that does not turn with the actual axle is to use some kind of sprocket. Okay, so if we're going to have a sprocket here, it needs to be powered by another sprocket. And if there's another sprocket, that sprocket is going to have to be tensioned in some kind of way. Now, I could have had an idler sprocket, a third sprocket that goes here, that moves up and down, and use that as the tensioner. That, well, could have worked, but I wasn't very comfortable with that idea because it would involve either having a kind of idler that is only supported by one plate. If you imagine the idler would be, let's say the sprocket driving this arm is over here. Maybe the next version shows this already. Well, this is a bit far along, but okay. Let's say the sprocket's here, and the other sprocket, that's the driver sprocket, is here, and I could have had an idler sprocket somewhere up here to tension the chain, forming some kind of triangle shape, right? If I did that, that sprocket would only be supported by one plate. Okay, that would be one option, and that would make it susceptible to bending downward because it's not fully supported. Or I would need to have a whole nother axle going across if I wanted to be properly supported by these two plates. Okay, and that picture didn't look very good to me, so I decided that instead of doing that, I could just make the entire gearbox itself shift for this second arm. Right, and that would mean putting a plate on some kind of slide. And so we have slot holes here, okay, and the cam holes on this version. So we're going to move on to the next version. To balance out the weight a bit, I decided that the motors for this second arm, and again, it's a 2-motor gearbox, as we can see due to all the calculations here, and it needs to use these ratios to get what we want, the desired effect. Okay, the 2 motors are on this side to balance out the weight, since 2 heavy motors with their planetary gearboxes are already on that side, and then that means the pneumatic brakes have to be on this side. Okay, straightforward enough. The cutout holes have the same position for these slot holes. Okay, that's the similar, but the inner outline that you see here is not the same between these 2 plates. Why? Because they don't need to be the same. Simply, the mounting structure is not the same for both sides. here we need to put 6 bolts to secure this pneumatic brake. Okay, so there's these 6 bolts, and there's basically a hexagon moved to the left by 0.5 inches because that's as far as would ever need to go. Okay, so we have a hexagon shape kind of up here with this edge extended so that it can facilitate the transversal of this entire gearbox in that direction. If I can demonstrate as such, you know, maybe it's 0.2, I don't know, whatever. It can move some distance, right? It probably can move 0.5. And you can see that it shifted over a bit. And that's where it was originally, right? And it needs to have enough room on this edge for the bearing hole here. That is going to be the axle where the driver sprocket is. Okay, so that's pretty similar on this side in terms of the front part. But the rest of it is not the same, simply because we only need, the way these max planetary gearboxes are designed is that you only have 4 mounting holes. So I only need to cover that much on this side. Okay, and the 4 mounting holes are in that kind of pattern. So considering that, and this one's rotated just so that it has a cleaner shape and doesn't get in the way of this slot hole. See, they're not in the same orientation with a 1, 2, 3, 4 pattern, and the same one down here is rotated 90 degrees just so it doesn't get in the way of the slot holes and maintains some symmetry between the 2 sides. Also doesn't get in the way of the 1x1s that would be sitting down here. I can't just move the slot holes lower if I want to keep the gearbox as compact as it is in this design. Okay, but this still facilitates the kind of transversal. Okay, I have the holes in this position, and then I just need to make the straight section extend out a bit so that it's possible for this gearbox to shift over as such. 0.5. Okay, and so you can see that it also works in the most far right position. So what does this do? We have slot holes. We also now have the actual hole where the cam goes, and that allows you to push this entire gearbox along that line, and that allows you to tension the chain between this sprocket and this sprocket. Okay. Why are the slot holes where they are? Well, the rule of thumb for a plate, well, L planes are formed by 3 points. So you have to have at least 3 points to properly secure a plate. So I wanted 3 connections on each side. So we need to have 3 slot holes. There are a few different ways to do this, but I decided that since I was going to put the axle for the sprocket closer to the primary axle where everything again has to go through, I could put the gearbox to the right a bit. And so that forms this kind of right, left pattern. And so to make it as compact as possible, I would do the opposite for the slot holes with this left pattern. And then from there, I just had to shape things so that it would actually work and try to just make sure that there was enough distance between various edges. Maybe this edge should have been a bit longer. I don't know. But yes, I tried to make sure that there was enough room between these edges so that it wouldn't be completely obvious that the metal would get warped and that the bolt would be able to fall through or something. Because keep in mind, there's a chain connecting these 2 sprockets together, and essentially it, at some given point in time, would have a lot of force on it because it's powering this second arm's pivot. And you don't want the pulling force to rip the gearbox apart, so you want to just make sure that the plate can't be so easily tarnished. Now, these plates are aluminum, so it's a lot stronger than, I don't know what other option there really would be. I guess, yeah, stronger than the Delrin for sure. Yeah. Okay, so now we're going to talk a bit about sensors. I'm going to bring back in this sketch. I decided that at this point in time that it was okay to just not put the arm exactly in the middle, so it's actually a bit to the side, as you can see, because I wanted things to have a nice spacing between them. Okay, and that meant that if I put the sensor on one side and the sensor was not required on this other side, for down here, the gearbox of the first arm's pivot, that if I wanted things to be spaced evenly, that the whole arm would be shifted aside, and at the time I decided that was okay. However, I realized that I had not fully thought through everything, because where was I going to put the encoder for the second arm's gearbox? There wasn't a very obvious place, because one sprocket's here. Well, I guess I could have actually put it kind of there, maybe. But it would have issues. Oh, I'm hiding gears, that's why. Show all components. Yeah, that wouldn't even be an option. There's gears here, so I couldn't put the sensor there, and there's not enough room on this side between the sprocket and the plate here to actually fit the sensor inside. So this wasn't really going to work. Another thing that I can touch on here was that I already decided to make the pivot just go straight off of this bottom arm, and then have the pivot kind of come down from the second arm in this kind of shape. The reason for that was that in one position it could be here, but by not making this edge align with the first arm, it would actually give it a greater degree of mobility and be able to rotate all the way around 270 degrees, which I can show at the end, I suppose. Okay, so moving on. Considering I needed to make more space for the sensors on both sides, I decided that I would again try to align the stock for the first and second arm towards the middle, and just figure out some way to cram in all of these gears. And so that meant that instead of double layering the gears in a standard way of putting them beside each other, I had to instead split them up with one layer of gears here and another layer of gears here. This is still double layering the gears and distributes the force more evenly. It's just, well, required a bit of restructuring. The physics works out that it's still effective at accomplishing that and preventing the gears from shearing. Okay, so with this setup, there is now a lot more room between various components, which makes it more possible to fit in some kind of sensor here. And I'll touch on more details that are now present in this version of the design. We do not yet, so to go over this again, these two sprockets would have a bearing here. They would be connected to each other so that this sprocket can be powered by the second arm's gearbox, okay? And by having the bearings inside these sprockets, these two sprockets, while they turn with each other because they have standoffs between them, would not turn and follow the axle. So they're being kind of powered separately. This in turn allows for these two sprockets to be powered, okay, by a chain running across. And this sprocket is directly mounted onto the second arm's pivot by these standoffs here, okay? And that allows for the second arm to, well, function properly. Now again, this is another chain that is running across here, and with every chain, you cannot just rely on a chain calculator to know the correct distance to put between the two sprockets so that the chain is tensioned. Chain will stretch over time. I mean, belts with pulleys can also stretch, so ideally you also have tensioners with belts and pulleys, but belts and pulleys are also usually not used under high torque applications. We use chain because chains are stronger, right, for these kinds of mechanisms. So considering that I needed some kind of tensioner, so I decided again I was going to put this entire pivot point on a slide. It's not fully developed yet in this version, but it will be, and have a cam that pushes the slide backwards and forwards so that this entire second arm with the second arm slide gearbox. What is this under? Okay, it's not in its own component. The second arm, along with this plate for reference, would be able to just travel along this path, right? And that, okay, not by that much, like a tiny increment, right? By turning this cam, which allows you to tension the chain fully. Okay. Oh, I do spot the encoder. So I decided to put the encoder for. What is this for? Okay, this comes up later. So this is actually the encoder for the slide. So let's go on to the next version. Okay, so now we have the encoder for the second arms gearbox down here. It's running off of one of these input shafts that is then powering the gearbox, which then powers this sprocket again to just lay it all out, which then transfers to this sprocket, and these two sprockets have standoffs between them, so that now a chain running all the way across to this sprocket can be powered, which then turns the arm. Now, if you notice, they're all using, beyond the very first driver sprocket, the rest of the sprockets are the type that allow you to put a bearing inside. The axle way of running across this pivot is actually not turning with the sprocket, at least not strictly. It doesn't have to, because it's actually going inside two bearings, which are smooth turning. So this introduces the third encoder that we have here, which is going to be used to measure the slide's action. So talking about the slide, at this point I realized that I needed to try to add on the slide gearbox, and while I had thought it out mostly, I kind of just figured I could put it somewhere in the front half of the gearbox, if I'm calling this side the front, above the first arm's gearbox motors. In an earlier version, okay, I was experimenting with the shape of the plate. I was trying to figure out how can I mount the slide's gearbox here, so you can see that it was in this kind of shape. And then I decided to just keep it to vaguely this, what is this, a pentagon? 1, 2, 3, 4, 5 sides, yeah. This pentagon shape here, but just raise this side a bit higher so that I could fit in these slot holes that would allow me to attach on this gearbox. Okay. Admittedly, this gearbox is not the best supported one. It's just running off one plate. It does have the potential to bend around a bit. But considering the kind of torque that is applied, we are not trying to drive a system that has a really far away like center of gravity relative to the pivot, right? The ultimate goal of this is to turn some kind of pulley that has string wrapping around it, and the string just pulls on the lift. So there's not as much like torque applied on the final mechanism. So that's why I'm not using as beefy sprockets. Instead of these number 35s used for the second arms gearbox, I'm using these number 25 sprockets. And also the final output I decided was using a pulley was acceptable. Keep in mind that for this design, we actually have not built it yet as I'm saying this right now, so who knows if it would actually work, but it's also pretty easy to just swap this out for sprockets in the event that, well, it actually wouldn't be entirely easy. Okay, more on that later. So next thing, right, we have this new gearbox here, and I decided that it would, following again the guidelines of the gear ratios we need for the slide. Okay, there's one stage and then there's a second stage. I just need to make one stage gearbox here, and then it runs off into a pulley. Okay, so this pulley then drives this pulley, and these two pulleys have standoffs between them, and so that allows you to transfer power all the way to over here, where again this pulley sorry, not pulley, what am I saying? This sprocket can be powered by this sprocket, just to be super clear on that. Okay, and again, this can be tension because we have the cam sliding this section backwards and forwards. Okay, so hopefully we can get all of the different parts tensioned properly. And then from there, it would have been possible to set up some kind of like additional pulley or maybe sprocket to tension this point properly, but considering that it's static and I didn't have a very good way to make another moving plate that I felt was strong enough to support the second arm since it's so long and humongous, I figured that the best thing to do was to use pulleys because you can more accurately rely on the pulley calculator for the distance between these two pulleys and just put the correct length belt on, and it's pretty likely to work. So that's why I use pulleys there. Okay. So moving on to the very final iteration, we just got some things jointed so I could actually show some of the different various tensionings techniques a bit more accurately, and we can just finish off with how this whole rope system actually works. The idea is you have a pulley inside, a screw comes out through here so that you can actually screw down the pulley to lock onto one of the 6 faces of this axle. This axle is turning with this pulley, right? And this pulley is turning also with this pulley because this pulley has, again, a hexagonal inner bore, so it turns with this axle, which is turning with the sprocket, leading all the way back to the gearbox, which I already explained fully. Okay, so up here, we have 2 ropes. One rope runs off of here and is tied to the bottom of this sliding system. Okay, another rope follows this pathway of going out through this hole that you can see here, around this pulley. Now, it doesn't even need to be properly spinning. Ideally, it would be, and this wouldn't be so tight. But even if it was tight, and this is just a smooth surface for the rope to go over, it should function fine enough. And then the rope goes around this bearing here, it goes back down through that gap all the way to tie at the bottom of the slide. So to touch on that, okay, we can see the slide moving. Okay, so I can then move the slide inwards and outwards by pulling these 2 ropes. When it's moving to the right in this orientation, right, the rope that goes all the way around and back in that ties to the bottom is the one that's pulling. And when it goes the other direction inwards to the left, the rope that goes straight from the pulley to the bottom of the slide is the one that's doing the pulling action, and it allows you to then power that slide properly. Okay, so that's all of it integrated, and just to make it very clear with all these with the final version of this massive gearbox that we have here, just going to go over things quick succession. Okay, we have the first gearbox is all of these components down here, which I guess I included the static plate that the second gearbox is mounted on. And by first gearbox, I mean the gearbox that is powering the first pivot. Okay, so it turns the arm around the pivot point down here. Okay, so we can see that in action. All the gears turning. Okay. From there, we have a chain running off of the second gearbox. Okay, so there's some gears here. That's pretty standard. And then you have a chain running from this sprocket to this sprocket. And the sprockets are also double layered. Not that it was entirely necessary, but I felt that powering this mechanism from both sides would make it function better instead of putting the strain on one side. Sprockets, though, do not have the same potential issue of shearing to pieces like gears do, just to be clear about that. But balancing the force applied on both sides, I felt was still a relevant thing to do. So that's why there are sprockets on both sides. Okay, so we have the two sprockets actually with the standoffs now, so you can see that they're joined together. So these two sprockets would turn together. And then that runs all the way to over here, turning this sprocket, okay, which then allows us to turn the second arm around that pivot down there. Okay, and to show you that 270-degree action, because I have this edge all the way over there, right, it can turn all the way to 270 degrees comfortably. It could even turn more, arguably, but that is how it is designed for now. Okay, if it was the same, if it lined up to this edge properly, like the front over here, it, as in like this whole, like this pivot was directly above this pivot, it wouldn't be able to quite make it all the way around 270 degrees, but now it has that ability. Okay. And for the final series of gearboxes, we have the slide gearbox here, which runs a number 25 chain off to this sprocket. These two sprockets are joined together by standoff, so they turn in succession, and the chain goes all the way over to this sprocket. This sprocket no longer has a bearing inside, so it actually turns with this axle, which allows it to then turn this pulley on this side, which by powering this pulley actually powers the rope pulley that moves the slide backwards and forwards. So I know I might have repeated myself a bit, but it is a rather complicated gearbox, so I just wanted to make certain points very clear. Key things to highlight, using this ability of these types of sprockets to just put a bearing inside allows them to turn independently of the axle they're mounted on, allows you to do these kinds of interesting multi-axle arms. Not really sure of another effective way to do it, honestly. If you didn't have these gears, it might not be possible. And the other things to know is that whenever you have chain, you always have to think about tensioning the chain. So that's why there are these cams with this gearbox. That's why this whole section of the gearbox can move, direct joint, can move, right? It's tensioned in such a way. Okay, and you always got to think about making sure that components aren't getting in the way of each other. So that's why there's like a little cutout here. And it all, well, came together, which is the most largest file in this final design. And it's kind of the cornerstone, which makes the actual project actually have a, in theory, usable design. So hope you learned something. See you in the next video.